So good evening, all of you. Today, today I will like to present you a lecture on introduction to machine foundations. And right away, I will share my screen. So this is the topic of my presentation. It is Introduction to Machine Foundations. I am Dr. Jayamohan, Professor in Civil Engineering, LBS Institute of Technology for Women, Thiruvananthapuram. So this is the contents of today's presentation. I'll be giving you a brief introduction to machine foundation and about some theoretical aspects of mass spring model for undamped free vibrations. Then we will discuss about the parameters like natural frequency and coefficient of uniform elastic compression. And also we will discuss about some methods of vibration isolation. Now, usually, commonly we discuss about machine for foundations for buildings, foundations for bridges, and foundations for other structures where the loads are only static in nature. But when we come to industry, we have got lot of machines which work in various different ways. These machines may create vibrations or may create periodic impact forces and lot of other movements. So here, these foundations, in addition to static forces, they are also static forces and static moments. These are also subjected to dynamic forces, and here then lot other parameters like amplitude, frequency, resonance. All these are to be taken care of. Anyway, I will show you some photographs. So here, this we can see a huge machine like this, and this is the concrete foundation supporting that machine. And then this is another machine. You can see and it is just bolted to a concrete foundation. Now, the dynamic forces which act on a foundation may be due to various aspects, maybe due to the vibratory motion of machine, or in the case of a bridge, maybe due to movement of vehicles. And sometimes there are machines which create impact forces, we call as hammers, could be due to impact, or may in the case of buildings, maybe due to earthquakes or dynamic or winds, or in the case of offshore structures, the dynamic forces may be due to waves and maybe due to nuclear blast in certain industries or inside mines. We have explosions inside mine, and especially wherever pile driving is being carried out, we have the dynamic forces due to pile driving operations. So these are the various reasons due to which soil is subjected to dynamic forces. Now, when we talk about machines, commonly, based on the nature of forces they transmit to foundation, we classify them into three categories. One is machines which produce periodic unbalanced forces. The most common examples are the reciprocating engine or reciprocating compressors. And now I'll show you a small video of a reciprocating machine. You can see
inside the cylinder, and this motion accomplishes the suction and discharge of liquid. The reciprocating pump works on the principle of positive displacement. It consists of a piston that moves back and forth inside the cylinder. The piston is connected to a crankshaft with the help of connecting rod. When the motor rotates the crankshaft converts the rotary motion into reciprocating motion, and this reciprocating motion is transferred to a piston using the connecting rod. Therefore, the piston starts reciprocating. During this motion, when the piston moves back in the cylinder, it creates a low pressure inside the cylinder. Due to this low pressure, the water from the tank is sucked into the cylinder.
So this motion of the piston, the crank, and the connecting rod, that will create a periodic unbalanced forces onto this foundation. Anyway, we'll go back to the PPT. So that was about reciprocating engines. So that creates a periodical unbalanced force. Now, second one is machines which produce impact loads, like forge hammers. So these are machines which create periodic impact loads. Anyway, we will see a forge hammer now. Yeah, this is a forge hammer. You can see here you can see a hammer which is continuously falling on this bottom part. So this impact due to this hammer will cause periodic impact loads. So we can see the video once again. So below is the machine. Here we have the machine, and below we have the foundation. Below here we have the foundation, which is subjected to continuous impact loads. Okay, we'll go back to PPT. Now, third are high-speed machines like high-speed turbines or rotary. These huge turbines. So usually these are they are providing hydropower units and all. They create huge vibratory motion and vibratory loads. Now, when we come to the first case, machines which produce periodic unbalanced force. The speed is usually less than 600 RPM, and that produce an unbalanced force sinusoidally that follows a sine wave. Most common example are reciprocating engines and compressors, which we saw the video. So this is the picture of the video which we saw just now. This is a typical reciprocating engine. Then machines which produce impact loads, as we saw just now, like forge, hammers, etc. So this another hammer, you can see this will rise and fall down, and the foundation will be below this concrete foundation, which is subjected to periodic impact loads. So the working of this hammer we saw just now as a video. So the effect is to create a periodic impulse or impact loads. We call it as a pulsating curve. That high-speed machines, the speeds are very high, frequency is very high. It is more than, sometimes it can be even more than 3000 RPM, 3000 rotations per minute. For most common examples are turbines and rotary compressors. This is a typical huge turbine, as you can see. Now, when we come to the foundations of these machines, what are the types of foundations? Based on the nature of the machine, based on the magnitude of the static force, based on the frequency and amplitude of the dynamic forces, the type of machine is chosen, and also based on the functional aspects of the machine, the foundation is chosen. Foundation can be either a block type, or a box type, or a wall type, or even a framed type. We will briefly discuss about the various types of these foundations. This is a typical block type foundation. You can see this either a concrete or a masonry block, and above that we have the machine. So this is the machine, as you can see at the top. Below we have a pedestal with the base. That is a machine foundation. You can see a photograph of a typical box type, a block type foundation. This is a typical block type machine foundation. You can see two huge concrete blocks, foundations made of concrete blocks. So fundamentally, that is a pedestal resting on a footing. The peculiarity of block type foundation is the mass is large and its natural frequency will be less. Next comes a box type. Box type means above we have the machine and there is a concrete box supporting the machine. Inside portion is hollow. So this may be due to various reasons. For maintenance purpose and all, we may have reached the bottom portion of the machine, or for connections, electric connections, or maybe some machines may require fluids or gas. So for this connections and all, and for maintenance purposes, so bottom portion will be hollow. These are known as box type machine foundations. And sometimes To alter the natural frequency, we may have to reduce the mass of the foundation. So for that also box type may be given. So its mass is less, so frequency will be more. If you want to increase the natural frequency of the machine, you have to reduce its mass. So this is a typical box type foundation. You can see the hollow portion. Another photograph of a box type machine foundation being constructed. This another box type machine foundation. Here you can see the bolts. So the bolts which will be used for connecting the machine. Third type is a wall type machine foundation. So there are either 2 or 3 walls. So there's a concrete base slab. Over there are 2 or 3 walls. Above that there is a slab, top slab. Above that we have the foundation. So these type of foundations are provided, for functional reasons. Sometimes the operator may have to go beneath the machine to operate it, or for doing maintenance. The maintenance engineer has to inspect the machine from below. In such cases, for some functional reasons, we may require to provide a wall type of foundation. Then fourth one is a framed type. Here instead of wall, bottom we have a slab. Top we have, then on all sides we have concrete columns. Concrete columns. The top they are joined together by horizontal beams. So horizontal beams. Over that the foundation is placed. Bottom portion is open. Here also we can inspect the machine from below, maybe for maintenance reasons or for operational reasons. So anyway, based on the functional requirements of the machine, the type of foundations chosen. Also from civil engineering point of view, the major parameters are the weight of the machine, plus the frequency with which it operates, plus the maximum amplitude of vibration. All these are important parameters for this. Yeah, these are the aspects of frame type machine foundation. Now the general criteria for the design, there are some criteria. So for as in the case of foundations subjected to static loads, here also the foundation must be safe against shear failure and settlement. So it should be safe against shear failure and the settlement must be within the allowable limits. Then the most important thing is there should not be any possibility of resonance, because the operating frequency of the machine and the natural frequency of the foundation should never come close to each other. If they come close to each other, it may cause the phenomenon called resonance, where the amplitude will be very high and definitely it will damage the foundation and the structure. So these are things. So and the amplitudes under service conditions should be within permissible limits of the machine. And more importantly, the center of gravity of the machine and the center of gravity of the foundation must lie on the same vertical line, so as to prevent differential settlement. So these are that is very important aspect. And the machine, so near to the machine, there may be adjacent structures. The vibration of the machine will be transmitted to the adjacent structures through the soil. So to prevent that, preferably machine foundation should be at a lower level than the foundations of adjacent structure. We have to provide proper vibration isolation in a way that we will discuss at a later stage regarding vibration isolation. And if there is groundwater is there, the foundation should preferably be above the groundwater. That is mentioned in the last point. Now coming to the degrees of freedom, as you know, in basic mechanics of solids or engineering mechanics, we learn about it. That's a number of independent coordinates required to describe the motion of the system. And I have demonstrated 2 cases. First one is a 1 degree of freedom. Second is a 2 degrees of freedom system. Now a system with n degrees of freedom will have n modes of vibration and n number of natural frequencies. So that is the most important aspect here. Now, when we talk about a machine foundation, it is usually a 6 degree of freedom system. So along all the 3 axes, along each, we have a 3 axes, X, Y, and Z. And along each axis, we have linear motion. Also, we have rotary motion. So So these are the degrees of freedom of a block foundation, translation along X, Y, and Z axis, and also rotation about X, Y, and Z axis. So there are 6 degrees of freedom for a typical machine foundation. Now, natural frequency. The frequency of a system under free vibration, we call it as natural frequency. So, when a body vibrates under free vibration, the frequency, that frequency is known as natural frequency. So, one system may have more than one natural frequency depending on its degrees of freedom. So, this is a typical mass spring model for undamped free vibration. So, this is the rheological model. Here we have the mass, and here we have the spring with stiffness K. M is the mass. So when there is no damping, so this is the mode of vibration. Of course, these are the related equations. This Fn is the natural frequency, and K is the stiffness of the spring. M is the mass. Fn is the natural frequency. And here we have discussed about a parameter called coefficient of elastic uniform compression. It is the compressive stress causing unit elastic uniform compression in a given area under dynamic loading conditions. So mathematically, it is defined as the ratio of compressive stress to the elastic part of settlement. You know, when we apply a compressive stress, soil compresses, some of the compression or some of the settlement will be elastic, some of and the remaining part will be plastic. So the compressive stress applied to the elastic part of settlement, we call it as coefficient of elastic uniform compression. So this is the equation for natural frequency again. Now you see, when you have a building or an industry nearby to your house, when there are machines working in that industry, when the vibrations are transmitted to the ground, through the ground they get transmitted to your building, you will feel uncomfortable because of the vibrations. So now, quite obviously, if you have an industry, if you have a machine, you must take care that the vibration created by your machine does not get transmitted to your neighbor's property. So that this process by which we isolate this vibration is known as vibration isolation. So here they have represented, you can see a locomotive, a train passing through a railway track. You can see the vibrations passing through the ground, reaching the nearby house. You can see the person residing in the house is getting irritated. So this is a simple representation of the transmission of vibration to adjacent structures. Now we have to prevent this transmission of vibration to the adjacent structures, for which we go for vibration isolation practices. Now transmission can be controlled by 2 types of isolation. Active isolation means isolating it at the source. You are not allowing the vibration of your machine to go out of your premises. Then second is passive isolation, that's protecting the receiver. You are isolating the receiver or isolating the neighbor so that your vibration doesn't reach him. There are 2 types of are possible. So maybe what we can do, these are various methods of isolation. Either the machine foundation can be located far away from the adjoining structure. We call it as geometric isolation. Or we can provide additional elements, additional masses called dampers, so that it will bring down the vibration. Or we can provide vibration absorbing material between the machine and foundation, like rubber or cork, so that they will absorb the vibration. Or the propagation can be prevented by providing trenches or sheet piles. So these are some methods of vibration isolation. Here, this is a huge building. There's a damper inside. So you can see that ball type structure, such heavy ball. When due to heavy wind or earthquake, when the building sways to one side, the damper will move to the opposite side. So thereby it will reduce the vibration or amplitude of vibration in that building. You can see here there are machine foundation below. There are springs. I hope you can see these springs. These are used for damping, so that these springs will absorb much of the vibration and they will not get transmitted to ground. This is a typical rheological model of isolator. So this is the machine. This is the unbalanced force, which is a function of natural frequency and time, or frequency and time. And this isolator, this is the foundation. Isolator is a damper which will prevent the vibrations from entering the foundation. So these are very common nowadays. These are two treadmills. You can see below there are dampers. There are elastic pads to absorb the vibration. So here, before the construction of foundation, they are putting this isolation pads. So this is some building in some other country. So you can see how they are putting the vibration pads below the foundation before concreting. So this is a typical symbolic representation of a trench barrier. So this is the location, or this is the origin of vibration. This is adjacent structure. Vibration is passing towards all sides. Here there is a trench. Here there is a trench, and this surface wave, or we call it Rayleigh wave, will not pass beyond this trench. So providing trenches is a very good method of vibration isolation. So with this, I end up this presentation. I hope you enjoyed the presentation. Thank you very much.